Hey guys, what's the crack? In this video, we're going to go over thermal energy transfer. Okay, so thermal energy transfer, we're looking at how the temperature of substance changes over time. Okay, we're transferring thermal energy. And we know that all substances, they have an internal energy. So what the internal energy is, and you need to know this definition. The internal energy is the sum, so again, we add them together, the sum of the random distributions of kinetic energy and potential energies. Okay? Kinetic energy, we know that's to do with anything that is moving, right? So we've got particles that are moving, we know they've got kinetic energy. And potential energy basically tells us about the space between the particles. For example, gas particles have a high potential energy because there's a large gap between the particles, where solid particles have got a low potential energy because the particles are really close together. The way I remember is think about gravitational potential energy. If something's really high above the surface of the Earth, it's got loads of gravitational potential energy when that distance is large. So when the distance is large, that's when we've got lots of potential energy, and when they're close together, we've got less potential energy. So the way that we can change the internal energy is there's two ways to change it. We can change the internal energy by heating it or by doing work done on the system. Okay, so there's two different ways we can change the internal energy, by heating it or by work done on the system. So heating it, we're going to look at here. And another one for work done on the system is, let's say I've got gas in a container. If I compress that gas, I'm doing work done on the gas. So I'm changing its internal energy. And this is called the first law of thermodynamics. That there's the ways to change the internal energy is by heating or by work done. Okay, so let's imagine we're doing heating. Okay, so I've got my ice cube, I'm going to heat it up with my Bunsen burner, and we're seeing what's going to happen over time. So let's say our ice cube is starting maybe like -10 degrees Celsius. Okay, so let's imagine here is my number -10 degrees Celsius. We know ice, and you need to know these numbers for water. Ice, we know, is going to change state at 0 degrees Celsius. So that flat line there always represents our change in state. You should have seen this from your GCSEs. So that's our change in state. And if it's a perfect flat line, we know it's because it's a pure substance. So imagine we've got pure ice, okay? So only H2O particles there. Okay, so again, change in state. The next change in state, we know for ice, for water, ice always happens at 100 degrees Celsius, okay? So that first change in state there is, we know if we're heating the ice up, that's going to be our melting. And if we're cooling it down, it's also going to be our freezing. If we're heating the ice up, this one is going to be our boiling. We change the state from a liquid to a gas. And if we're cooling the steam down, that's going to be our condensation from a gas to a liquid, okay? Any times we have these change in states, we know that we need to use the equation E equals m times L. So that energy equals the mass times the specific latent heat. Okay? This is how you write it in OCRA and in Edexcel. In AQA, for some weird reason, they like to use the letter Q instead of E. Okay? But in GCSEs, in AQA, you still use E. So I'm not really sure why in A-level decided to change it to Q, but just know that, and if you're doing AQA, the Q is just the same thing as the energy there. So again, what L stands for is our specific latent heat. Okay, so what is specific latent heat? Specific latent heat is the energy to change state of 1 kilogram of substance without a change in temperature. Right, we can see that because the temperature remains fixed when we're doing our change in state. And there's two different types of change state. We got our specific latent heat here due to fusion. So the way I remember fusion is when things get joined together. So that's why it's going to be from a solid to a liquid, or from a liquid to a solid. We always use the specific latent heat of fusion because the particles are touching. And if we're going from a liquid to a gas, or from a gas to a liquid, that's going to be our specific latent heat of vaporization. Okay, it's like vaporization. If you vaporize something, it becomes a gas. Okay, so what we're doing then is, let's look again at the start. So what we're doing is we have our ice and we're heating it up. Our ice is increasing in temperature from -10 to 0. So as we're increasing the temperature, what's happening here is we're increasing the kinetic energy of our particles. So what happens is here from -10 to 0, we know it still is a solid, right? It's still a solid, but we're increasing the kinetic energy. The particles are vibrating faster and faster and faster. And that energy then that we're increasing is our specific heat capacity, sorry. So that energy there is M times the specific heat capacity times by its change in temperature. Again, if you're doing AQA, they like to use their Q here. Okay, so energy is mass times the specific heat capacity times by that change in temperature. So anytime we're increasing the temperature or changing that temperature, we're increasing the energy, we're increasing its kinetic energy. Anytime then we have a change in state, we're increasing its energy, we're increasing the energy because of the specific latent heat. Then once we change state, and when we're changing state, because we're changing from a solid to a liquid, we're changing the distance between the particles, what we're increasing here is we're increasing the potential energy. So when we have a change in state, what we're increasing again is our potential energy. Again, from 0 degrees to 100 degrees, we're now in a liquid. And what's happening is our particles are moving faster and faster and faster. So again, we're increasing their kinetic energy. And then we have a change in state. Because that change in state, again, we're changing from a liquid to a gas. We're changing the distance between the particles. Again, what we're increasing here is we're increasing the potential energy. So we're increasing the potential energy. We're separating the particles more. Once it all becomes a gas, again, if we keep increasing that temperature, we're increasing the kinetic energy again of those particles. So key facts is anywhere that we're increasing the temperature, you always know that we're increasing the kinetic energy, and we use this equation involving specific heat capacity. There's going to be more about this in the next video. And anywhere there's a change in state, we know to use this equation because there's a change in state. We use the specific latent heat of fusion, or the specific latent heat of vaporization, which is the energy to change state of 1 kilogram substance without any change in the temperature. And what the energy we're changing here is that potential energy because we're changing the distance between our particles. So hopefully you find this helpful. So in this video that I do have my mic on for, go again.